Hey, how are y'all doing? Hopefully everybody is doing well. Today what we're going to be doing is finishing up our Unit 3 notes, and we're going to be covering our EM spectrum and light calculations. Now for this lesson, we are going to focus on the EM spectrum, and then there will be another lesson on light. All right, so for this, you do need to make sure you've got your notes, and you will need something to write with, specifically so you can take your own kind of jot down your own ideas on what we're talking about. Okay, so for the EM spectrum, first off, we need to know what the EM spectrum is. Well, it is a spectrum of electromagnetism. So what does that mean? Well, a spectrum is essentially a line. It is a line that kind of shows a generalized trend that we see. An electromagnetic radiation would be the radiant energy that's going to exhibit a wave-like behavior. Okay, and so that wave-like behavior is actually going to be going at the speed of light. So it is very, very quick. Now, here's something I will state about electromagnetic radiation. When we talk about it and when we do the math and when we solve problems for it, we are making the assumption that it is in a vacuum. Now, this is kind of the same thing as talking about the ideal gases, right? We talk about an ideal gas, and we know that in the real world, gases don't act ideally. They don't act the way that they should, but it is the best way for us to get an idea of how they should be acting. Same thing when we're talking about the electromagnetic radiation. When we do these calculations, we are going to make the assumption that it is the vacuum with the knowledge that we know that we're not in a vacuum. We're just not thinking about it in terms of how that would affect the light, okay? Or the electromagnetic radiation. Okay. So here I've got my spectrum. And in the spectrum, I've got frequency and I've got wavelength. And there is a relationship between frequency and wavelength. The longer the frequency, so the higher the frequency, or the longer the wavelength, the lower the frequency, and the higher the frequency, the shorter the wavelength. So they're going to have an inverse relationship. And so that's kind of something that you can keep in mind. If I'm talking about a very long wavelength, I know that its frequency is going to be very low. And then if I'm talking about a very short wavelength, it's going to have a very high frequency. Okay, now we also have a relationship with our energy. We know that if I've got a high energy, I've also got a high frequency. And so there is a relationship with our frequency and energy being directly related, but energy and wavelength being inversely related. Okay. All right. So this kind of gives you a general idea of how large these waves actually are. So if I'm talking about something like a gamma rays are actually the size of about the size of an atomic nuclei. So just the protons and the neutrons of an atom. So they are very, very, very small. Whereas if I'm talking about something like a radio wave, they are actually as long as like a building is tall. So they are very, very long. They can be thousands of meters long. And so we do kind of need to keep that in mind when we're talking about these wavelengths, because they can span such a broad range of lengths. Okay. Now, for chemistry, the big thing that we are looking at is how these waves, how this electromagnetic radiation is actually going to be affecting an atom. Okay. Now, we have talked about, in your previous chemistry course, you should have talked about the effect that light can have on an atom, specifically talking about how those electrons are going to be moving and emitting light. And we'll go over that here in a second. One of the things that you probably did not talk about are the effects that stuff like microwaves, infrared radiation, and then UV and X-rays, what they are going to do to an atom, to a molecule that we've got. So what are they going to do? Well, if I'm talking about a microwave, what microwaves do is they actually cause an atom to, or a molecule to spin, all right? And so it's going to be spinning. So it's going to change its rotational level is what we call it. If we're talking about an infrared radiation, what it's going to do is cause a molecule to vibrate in place. And then we will actually use UV and X-rays for photoelectron spectroscopy, PES. We've talked about that a little bit already. And we're going to use that to help us figure out what the electron configuration is for individual atoms. Okay? All right. So this chart right here kind of shows all of that, but I did want to show y'all an actual simulation of this actually occurring. So I'm talking about carbon monoxide, and I'm going to shoot some microwaves at it. And so we're going to hit play. And what do we see here? So it's shooting that out, and sometimes that molecule is actually absorbing the microwave. Okay, so we are absorbing the microwave, and as you see, it's changing the rotation of that molecule. Sometimes it rotates clockwise, sometimes it rotates counterclockwise. Now, what would we expect to see with our infrared? Well, we know that infrared should cause it to vibrate in place. So let's change it to infrared. All right, so infrared, it absorbed that energy, that molecule is vibrating in place. Eventually, after a certain period of time, that molecule will actually release that excess energy, and it will kind of float off into its own direction. But you do see that actually absorbing and vibrating in place. Now, let's look about visible light. So visible light, well, we didn't talk about its effect on a molecule because, as you can see, even sped up, it just passes straight through that molecule. So visible light isn't going to actually affect the molecule. It might affect the electrons, and it will affect the electrons in that molecule, but otherwise it's not going to have an overall effect. Ultraviolet, same thing as visible light. So we don't actually see anything changing in the molecule, but we could potentially see something happening with the electrons individually. Okay? All right, now let's take a look at water. Okay, so here's a water molecule. Ultraviolet, what do we notice? Nothing's happening. That's right. So nothing's happening here. How about visible? What would we expect? Visible, we would expect it to, again, do nothing. And so that's exactly what we're seeing. How about with infrared? Well, infrared, we should expect it to vibrate in place. That's right. So there you've got your molecules just like wiggle, wiggle, wiggle. It is vibrating in place. All right. And then for microwaves, what would we expect? We would expect that rotation to occur. And so that is what we are seeing there, that change in rotation. Sometimes it's clockwise, sometimes it is counterclockwise. All right, now we're going to do one more. So I'm going to turn this off. I'm going to change over to nitrogen. I'm going to do this. Now, again, we've got microwaves here. So what would we expect? Well, we would expect it to rotate probably, right? So let's turn the light back on and let's see what happens. What do we notice happening? It's passing straight through. So why do we think that is? How is it different from a carbon dioxide or monoxide and a water? Well, looking at those two, those are compounds of different elements, which means they've got different electronegativities, which means the polarity of those molecules is different. Nitrogen is going to be perfectly nonpolar, right? There's no difference in electronegativity there. And so what we're seeing is that those microwaves are going to pass straight through. Okay. What about infrared? Same thing. Visible. Same thing. Ultraviolet. Same thing. Passes straight through because it is completely nonpolar. Okay, so polarity can have an impact on what these waves are actually going to be doing. All right, so that is the simulation. It's not letting me change. There we go. Of those molecules in terms of how they are affected by the different waves. So let's take a look at kind of who contributed to this idea of an EM spectrum. And the biggest contributor at first was Bohr. So Niels Bohr was the one who came up with this idea that electrons travel in an orbit around the nucleus. And so he did that using this whole thing, using atomic spectroscopy. So what did he do? Well, first off, we learned in the past that a prism could actually separate light. And so what we could find is that when we shine light through a prism of some variety, be it glass or a crystal or something like that, that it can actually cause those wavelengths to actually separate out, and that's how we get a rainbow. If we're talking about white light, so something from like the sun, it's going to produce a continuous spectrum. And so we will see all colors of the rainbow. But not everything has a white light. Not everything uses a continuous spectrum. And so what we do know is that we can actually take that spectrum and we can come up with something called a bright line spectrum. And that's essentially taking an individual atom or compound and looking and seeing, okay, well, it's releasing these different lights. So we're going to get different bands of color. So like if I'm talking about helium, helium's going to have a little bit of blue and somewhere between teal and blue and teal and yellow. And then there is some orangey red right there. And we keep on moving across. And so we're actually seeing these different colors being produced as a part of this spectrum. Okay. Barium, what do you notice? How is it different? Well, barium, we're going to have a little bit less of that deeper blue, and it's going to be more of a blue-blue. We don't have that in between blue and teal. We do have kind of a tealish blue, but now we've got some greens, and there's some yellows and some oranges, and then some orangey reds. And so we kind of see the spectrum that is developed. Now, is it a complete spectrum? Does it have all the colors? No, it doesn't. It is not a continuous spectrum. It is what we call a bright line spectrum. Okay? All right. So what Niels Bohr did was he found that the absorptions and emissions of light by hydrogen correspond to the energy changes of those electrons. And so what he did was that he proposed that electrons will travel in certain orbits, right? Okay, well, we know this, right? Because when we talk about electron configuration, we talk about how those electrons sit in different orbits. And so that's what Niels Bohr actually predicted. Now, he was actually able to do some math, and his research was fantastic for hydrogen, but it was not perfect, okay? And so why it wasn't perfect is it didn't relate to every single thing. And so his research kind of dwindled at that point. He didn't make any more progress at that point. And so no progress was made until Schrodinger and Labroglie came in and they actually worked on this new model. So they looked at this light and they're like, okay, well, what's going on? And what they found was that the electrons don't sit in a perfect orbit that follows the nucleus, but instead they are found in general areas, what we now call our electron cloud. And so they visualize that these electrons aren't in this perfect spot on the orbits like Bohr thought, but instead they actually have a generalized area that we would find those electrons in. And then they also talked about how those electrons, when they release that energy, it's not going to be a traveling wave like what you would see in the ocean. It's instead a standing wave. And so a standing wave would be something similar to what you'd see on like plucking a guitar string or a harp or something like that, where it kind of looks like it's staying in place. Okay. All right. Very last thing to quickly talk about is how those electrons are actually going to be moving and what's going on with our light. And so that would be talking about the ground state and excited state of electrons. So the ground state of an electron is going to be when an electron is at rest. It's when it is sitting on the ground. It's quote unquote ground. And so that would typically be translated as what is the electron configuration of something. And those electrons would be where we predict them to be. The excited state is where they've actually jumped to a higher energy level. And so now they're in a higher energy level, which means eventually that energy is going to have to be released because that's not where they're meant to be. And so when it's released, that's when we see that light being emitted. So when we talk about light being emitted by different atoms and we talk about that bright line spectra, how that occurs is we take a ground state electron, which is sitting in its normal orbit, we excite it with some form of energy, typically visible light, and then once that electron is excited, it jumps to a higher energy level where it will sit for a certain period of time, and then it will fall back down to where it was originally. When it falls back down, it releases that energy, and that energy is in the form of light. All right. Okay, y'all, so that is it for our EM spectrum. Let me know if y'all have any questions, but otherwise, y'all have a great rest of the day. Bye, y'all.